What is going on? I hope everyone's having a good day. Hope everyone's excited to do this Riemann Sums stuff. Here we got a nice question for you guys. Find the area of the region bounded by the graph of y equals x cubed minus 2x squared and the x-axis using Riemann Sums. So first of all, we want to look at step 0, which is take a second to think WTF they're talking about. So don't jump into step-by-step processes blindly without really having a good idea of what you're trying to do. Then you can create some steps and figure out what you want to do. Okay. First of all, we got to know, what does y look like? Okay, that might help. This looks like a cubic, so we might be able to piece that together. Think, how are we going to create a bounded region? I don't know right now. Like this cubic function is going to do its thing, and then the x-axis, so like I don't see how that's obviously going to create a bounded region. We'll have to look at what that cubic is. And then, of course, what is the process of finding the area through Riemann sums? Without that, we are screwed. So step 1. And once we do that, then we're ready to go into some steps. I've written these out. This is what I would do if I was doing the problem. So it might be valuable for you guys to think about that. Find the x values associated with the bounded region. Okay? Next, decide how wide each Riemann rectangle will be. So this is related to this third think thing. What is the process of finding area through Riemann sums? Well, we need to decide how wide the rectangles will be. We need to decide how tall the rectangles will be. And then we need to multiply the width by the height and add them up. Step 5, use our information about the closed form of sums to get a numerical answer and take the limit. Okay, that seems fair. Step 6, use fundamental theorem of calculus to check our answer. Fundamental theorem of calculus is very, very smooth. Very quick, so we can just do a quick check at the end. Just make sure we're on the right track. Okay, step 0. What does y look like? Well, if you head over to Desmos.com, you can just plug in that function into Desmos, and it will graph it for you. Okay, we don't have to do this. We're obviously not going to use this in our solution. We're not going to take a picture and put the picture in the solution and say, look, here it intersects at 2. But it does help us understand a little bit what's going on, and that's why we're doing this. So this cubic comes up, bounces off the x-axis at 0, and then pierces through it at 2. Okay, so right away you know that the formula for this cubic has to be x squared and then x minus 2, and then it has to be positive because it's a cubic that comes in negative infinity and then leaves out positive infinity. But you don't have to remember that. We'll be able to figure all that out later. How are we going to create a bounded region? Well, look, it actually makes a bounded region. This area in here, here's the picture of the Riemann sum estimate of that. That area is bounded by the graph of y and the x-axis. In fact, it's the only area that's bounded by that graph and the x-axis. So that's why they did not have to specify, because there is only one region that's bounded by the given information. Now, it's worth noting that when you take your Riemann sums, you're going to generate a negative answer because it's below the x-axis. But that's not what they're asking for. They're not saying integrate this function from 0 to 2. If they said integrate this function from 0 to 2, then you would tell that you would compute this negative value. It'll give you a negative answer. And you would tell them the area is negative blah, blah, blah. Or if you integrate it from there to there, you get negative blah, blah, blah. That's not what they're asking. They're saying, what is the area of the region bounded by these two things? So they actually want to know, how much paint will it take to fill this thing? Obviously, the answer can't be negative. The answer has to be a positive. So whatever value we get through our computations, we know we're going to be taking the absolute value of that. We're just taking the positive of that because they're asking how much paint does it take to fill that region. Okay? Excuse me. Find the x values associated with the bounded region. Well, let's look at our function to start. We get x cubed minus 2x squared. Okay, we want to know, when does that equal 0, because we're finding when it intersects the x-axis in this particular question. So we have this. We can factor our greatest common factor of x squared. That leaves us with an x minus 2. You'll notice if you redistribute this x squared in here, you're going to get back this exact thing. That's good, and that better be true. And now we can look at this and say, what values of x make this statement true? That's always what it means when they say solve. When they say find the solutions, it means what variable values make that statement true. Right now, the only variable solutions are when x is 0, as anticipated, and there's a double root there, which is why it bounces off the x-axis, and when x equals 2, because 2 minus 2 gives us 0. This agrees with our picture, so we can be confident, little mathicans, and press forward to step 2. Sweet, let's do it. Step 2, decide how wide each Riemann rectangle will be. Okay, Well, for this particular problem, our interval of integration will be of length 2 because we're going to go from x equals 0 to x equals 2. Okay, why do I want to know that? Fact 2, in every Riemann sum problem, we always split our interval into n rectangles of even width. Okay, so if I know how long I'm going to be integrating from, then I can find the width of each rectangle because I always divide it into n rectangles of even width. Using fact 1 and fact 2, each rectangle should be of length 2 over n. In this case, it's 2 over n because it's length 2. I want to split it into n, let me see if I can get on camera there, n even rectangles, which means we have to divide it by n. Divide 2 by n, and that's the width of each rectangle. Sweet. You can check if you did this right by summing up n of your widths. You better get back the interval length you started with. So we started with 2, we split it up into 2 over n. If we add up n of those, that's like 2 over n times n. The n's would cancel, giving back 2, which is exactly what we want. Phew. Step 3, decide how tall each Riemann rectangle will be. Okay, so let's just go through a few. This is how I piece together my brain when I'm confused about this. I start with the first rectangle, and I say, how tall is my first rectangle going to be? I'm going to go over 2 over n. I know that for the first rectangle. And then I'm going to go up. I'm going to use that right, I guess it's backwards in the camera. I'm going to use this right endpoint and go up to the function. And whatever that function value is, that's going to be the height of my rectangle there. All right, so if the width of each rectangle is 2 over n and we're starting at x equals 0, then the height of the first rectangle should be the function value of, well, I start at 0, that's corresponding to this x equals 0. And then I go over 1 copy of my 2 over n. And then I just see, what is the function value when I input that into the function? If you simplify this inside stuff, the 0 of course goes away. One copy of 2 over n just gives you 2 over n. Okay. When you plug that into our function, remember it's x cubed minus 2x squared. So I'm just doing x cubed minus 2x squared. This is the height of our first rectangle. Okay, if the width of each rectangle is 2 over n and we're starting at x equals 0, then the height of the second rectangle should be, and again, just a reminder, you don't have to do this first and second rectangle part. I just do it because it helps me understand what the hell is going on. So I'm starting at 0, I take 2 copies of 2 over n, and I want to know the function value evaluated there. That's going to give me the right endpoint of the second rectangle, and it's giving me that height there. So that's going to be the height of my second wonderful, beautiful rectangle. That's equal to f at 2 times 2 over n, because it's 2 times 2 over n. The 0 means nothing to me. I cube it, and then I take away 2 copies of its square, because that's the rule of this function. Okay, cool. So now I'm getting an idea of an arbitrary ith rectangle in the Riemann sums, and that's important. That's what you want to know. You want to know the ith, where I is some number between 1 and n. You want to be able to know what's the height of that rectangle. If the width of each rectangle is 2 over n and we're starting at x equals 0, then the height of an arbitrary ith rectangle should be I copies of 2 over n. Right? The first rectangle was 1 copy of 2 over n. The second one was 2 copies of 2 over n. The ith one is I copies of 2 over n. We start at 0. You plug that into your function, you get this. That's the height of your ith rectangle. Sweet. What we should do now is multiply the base by the height and add them up. If the height of an arbitrary ith rectangle is this junk, and the width of each rectangle is 2 over n, then it stands to reason that the ith rectangle has an area of the product of those two. Yeah, because that's the area of rectangles. Makes sense. I'm buying. Now we just got to add them all up and make sure we get all n of our rectangles. Remember that with Riemann sums, we always split our area up into n rectangles. Okay, area of all n rectangles. So the sum as I goes from 1 to n of 2 over n, which is the width of each rectangle, times the height of each rectangle. And we add up all of these from the first one to the nth one. Okay? That's the process of Riemann sums. Now, step 5, use our information with the closed form of sums to get a numerical answer, and then we take the limit as n goes to infinity. Right, so obviously this value here, if we just look at this thing here, that's not the answer, right? We have to evaluate the sum. So hopefully it's an easy enough function that we can evaluate the sum. Otherwise it's really difficult actually. Notice that if this was even like x to the 5, that this problem would be extremely challenging. They had to give you something of smaller power, which again, by the way, emphasizes the power of the fundamental theorem of calculus. Antiderivatives are very useful in finding areas. Okay, so I just rewrote what we had before here, and then if we the next step, you can factor out a 2 over n, because we're not counting n's, we're counting i's, so you can always factor out a 2, and n is essentially a constant in this case. And I distributed the cube here, so that you get I cubed, 2 cubed, n cubed, I squared, 2 squared, n squared. Aha, there's all that stuff there. I'm just trying to simplify to isolate the i's, because we're not counting anything but the I, so I want to factor out everything else. Okay, the next step, I just simplify this further. This is 8 over n cubed, and I just write it in front of the I cubed minus 2 times, just simplified this 2 squared over n squared, took it out. Now we distribute the sum. So the sum of this, notice there's 2 terms here, the sum can apply to both. You can distribute that sum. All right. So that means I'm going to sum this thing minus 2 times the sum of this thing. The 2 comes out of the sum when you distribute the sum into there. All right. The next one, it's nicely set up. The 8 over n cubed can just come out in front, and you're left with I cubed. Okay. And then the 4 over n squared can come out in front, and it's multiplied by the 2, which gives you 8 over n squared. And then it's sum of I squared. Now, the reason why this is advantageous is because we can just look up, if you type into Wikipedia, search for summation, it'll just tell you how to sum things like this. Okay, and it'll tell you how to sum things like this as well. And I think this should be in your notes also. So the sum of I cubed happens to be n times n plus 1 over 2 all squared. And then the sum of I squared is n times n plus 1 times 2n plus 1 divided by 6. So I just put those values in. That's the closed form. This is nice because we can take the limit of this. We'll actually be able to make sense of that. And I do a little bit of simplification here. I distribute the 2 over n into here and 2 over n into there, and I get this stuff here. Now, with taking limits, it's important to know that the only thing that matters when you're taking the limit of a polynomial, this is a polynomial here, right? Because it's going to be n, the highest power of n is going to be 4 on the top of this half, not the minus stuff here. We'll deal with that in a second. If you did distribute this and do the squared, you would get, inside this brackets, you get an n squared term, and then because you're squaring, you're going to get an n to the 4 term. So the power of that is 4, and then on the bottom, the highest power is also 4. You can see it's just n to the 4. When that happens, it's even powered, and you're taking the limit as n goes to infinity. The only thing that matters is the coefficient in front of the highest power. The other powers that are less than the highest power are going to be absolutely meaningless for large values of n. So you disregard them entirely, which is nice. It's handy. So here, the coefficients in front of the highest powers of n, on the top it's going to be 16, because this one, when you do it all out, it's going to be 1 still. The bottom is going to be 4, so it's just 16 over 4. That's it. You can do that whatever method you want. I suggest you do a bit more work on if you're submitting anything, because they probably will be questioning how you came to that answer, even though it's quite valid. For this one here, the coefficient is going to be, the highest power is going to be cubed, by the way, and it's going to be 16 on the top. No, not quite, because there's this 2 here, so it's going to end up being 32 over 6. And so you're going to get 16 over 4 minus 32 over 6 here, okay? Now, you'll notice that gives you a negative answer. We anticipated this. We just take the positive of that, okay? Now, the last step is to use fundamental theorem of calculus to check our answer. It's so fast, you might as well do it, right? So if you're integrating this function from 0 to 2, you just take an antiderivative. Any antiderivative will do by the fundamental theorem of calculus. x4 over 4 minus 2x cubed over 3 does the trick. Evaluate it from 0 to 2. So you plug in a 2 for all the x's, and then you subtract it by plugging in a 0 and plug in a 0 for all the x's. What do you get? If you do the math, you get exactly what we had before. Well, we had 32 over 6, which of course is then 16 over 3. 16 over 4 is 4, blah, blah, blah. You can check this math. And again, we anticipated the negative number, but they're not asking for that. They're saying, what is the area of that region? The area of that region is the positive of this. Okay, so I hope that helps. I hope you guys had fun doing this. Don't be afraid of Riemann sums. It's kind of the same thing every time. And yeah, so until next time, later.